Hi. It's really a great pleasure to introduce Nima Arkani-Hamed, who's going to give today's colloquium. So back in 1997, Nima exploded on the scene with large extra dimensions. That's when he was a graduate student. And since then, he has continued for 30 years to be a leader and a rock star, I might add, in theoretical physics.
Movie star.
Movie star, actually, literally a movie star. Let me put in a little ad. The Particle Fever, it's a great movie. And he's been leading in beyond standard model physics, amplitudes, he's leading in that. And one thing he's known for is his remarkable originality and his clarity of lectures, which I think people in the school understand what I'm talking about. And he's won numerous awards, the Gribov Medal, the Sackler Prize, Breakthrough Prize, Sakurai Prize, and he's currently at the Institute for Advanced Study at Princeton, and it's really a great pleasure and an honor to introduce Nima. Please go ahead.
Thank you very, very much. It's wonderful to be here. It's really fantastic to be at the school, of course, but I'm also really delighted to be able to talk about a subject that's very near and dear to my heart, which is the question of big new accelerators and the future of particle physics. And if you're a particle physicist in this room, then you know there's a kind of a background subtext behind this question of the future of particle physics that we'll come to in a moment. But before getting into any details, I just want to start off making the most zeroth order comment about why we're talking about accelerators, period. Why accelerators? And just to say the zeroth order answer, obvious answer first. Why accelerators? Large accelerators are the only direct probe of short-distance frontier in fundamental physics, and they've given us the most profound structural clues to the laws of nature over the past 120 years, really starting with the first quote-unquote accelerator collision collider experiment, which was Rutherford's experiment probing the structure of the nucleus of the atom, and certainly gave the most profound structural clues to the development of the standard model of particle physics. There's no way this spectacular picture we have of the way the world works, down to distances 1,000 times smaller than the nucleus of the atom and out to distances approaching the size of the cosmological horizon, there's no way we would have arrived at this incredible picture without direct input from experiment. This is not something that sufficiently smart theorists or an advanced artificial intelligence could figure out, just given the even clues of working with the structure of Yang-Mills theories. You really needed experiment to give huge clues for what was actually going on. So why do we need accelerators? Why do we go to the short distance frontier? Because we must, by this continuation of this historical trajectory that we've been on. And it's important to emphasize we still can. Nothing has changed in where we are now in the third decade of the 21st century with our ability to build accelerators compared to what has happened in the past. They're bigger than before, it's true, but they're not yet the size of the planet Earth. We don't have to enslave half of the humanity in order to build them, like the people building the pyramids did, okay? We just have to more or less analytically continue what we're doing. They don't even cost that much more than they used to cost. Of course, they cost more, but the world is getting richer at the same time, and the fractional cost of big accelerators compared to GDP has always been around 10 to the minus 4 for the last 40 years. Okay? And that's not changing now when we're talking about the big accelerators we're going to be talking about. I've deliberately decided not to talk about costs and politics and blah, blah, blah. We can talk about that too. It's not as interesting a subject as the physics, but it is a necessary subject to talk about. But just to get it out of the way now, we're talking about 10 billion in your favorite units, okay, for how much these things cost, and that's roughly order 10 to the minus 4 of how rich the world is now, or how rich it's going to be when these things might end up being built. We are now talking about possible accelerator projects beyond the LHC that involve electron-positron colliders that would be used as Higgs factories, proton-proton colliders that would go to energies roughly 10 times higher than the Large Hadron Collider, so 100 TeV colliders, and the new kid on the block is the possibility of talking about muon colliders, and we'll be talking about all three of them today. But most of the colloquium is going to be spent talking about the physics reasons, the more concrete physics reasons for actually going beyond this zeroth order obvious reason that we should keep on going. We go because we must and we can. But the subtext of this discussion is the future of particle physics, and whether explicitly or implicitly, most particle physicists thinking about the future of particle physics are actually thinking about, is there a future of particle physics? Okay? And I think this is a completely reasonable question. In our field, we should not be afraid to ask any questions as explicitly as possible. It's not axiomatic that you should keep going just because you've done it in the past. Other people are thinking about this question. We should think about it ourselves. It's a totally reasonable question to ask. 10 billion is a big number. Even if it's 10 to the minus 4, you could spend that 10 to the minus 4 on other things. Completely okay to wonder whether we should stop, take our ball, and go home. Okay? Now, I think we should not. I think the stakes are so high that in many ways, the nature of the questions are more dramatic and more interesting and more fundamental than they've been in the past, and it's a spectacularly bad time to stop. But it's perfectly okay to raise the question and wonder about it, okay? And the counter to this point of view, which is what some fraction of people outside particle physics, and I should say a decent fraction of people in particle physics, kind of think this. And if some of your particle physics friends look a little bit depressed or, they're moaning a little bit, this is in the back of their mind what they're moaning about. They say, look, we saw at the LHC only the Higgs particle, nothing else. The Higgs, so either way, pretty boring. It just confirmed a 50-year-old theory. So boring, yawn, right? It's so boring, right? That's all. We haven't seen anything else. And then they might go on to say, and then with just the Higgs and nothing else, we're not going to convince politicians to build another accelerator. It's going to be very hard. I've always thought this argument is hysterical, that we can't convince politicians. I'd like to imagine some politician sitting in the US in Congress saying, I wonder if the notion of Wilsonian naturalness was actually proven wrong by the LHC, so we should not build the next collider. Give me a fucking break, right? They don't know anything about anything, okay? They're not the ones who know whether it's exciting or not exciting. The people who make this argument, the real problem is that they themselves think that it's not exciting anymore. They themselves don't see the point, and they feel a little bad about it, so they want to blame the politicians for it. Politicians have zero idea whether it's scientifically interesting or not. It's up to the scientists to tell them what is or isn't interesting. So that's what I want to do today, really mostly, is tell you what I think the scientific issues are and why I personally think it's ridiculously exciting and extremely important to keep on going. But it depends on your attitude, what you want out of the subject, whether you do or don't want to be alive to see a bump in a plot that will take you to Stockholm. Okay, I don't care so much. Stockholm's nice. There are other nice places in the world. I don't care so much about a big bump in a plot that takes me to Stockholm. That's not the reason I've been in this business my entire life. And I'm totally happy to work on questions that I have no idea what will happen when they come to fruition. It might take decades, centuries. I don't care. I'm totally happy to devote my life to questions that are going to find a resolution beyond the horizon of my own mortality. Other people can have a different attitude toward it. I'm not making a judgment about it, but we have to realize that if we're in this business, we're in it for the long haul. And if you are in it for the long haul, I want to tell you what I think the stakes are and why it's absolutely imperative to keep on going. Okay, so I want to explain why this picture is wrong, that we've seen the Higgs and nothing else. And so the first part of this colloquium is going to be about the Higgs. I want to tell you why the Higgs is special. And this is not hype, I promise you. Okay, this is not that we discovered it, we have to make a big deal about it, but secretly we don't actually think it's that exciting. At least not for me. The Higgs is incredibly interesting, and it's really new physics. It's new physics in a much more profound sense than had we discovered some strong interactions, technicolor, bunch of resonances, some fraction of people would have been their greatest dream. I would have been super depressed if something like that happened, because we would learn nothing essentially new about the way nature works. We would find just a repetition of the same patterns we've seen elsewhere in particle physics and condensed matter physics and so on. The Higgs is totally unlike that. We've never seen anything like it in nature before, and it's more fundamentally new physics in a more profound structural way than other things that we've seen in the past. And that's the first thing that I want to explain. So I want to spend the kind of first half of this colloquium explaining the content of this slide. The Higgs is really new physics. It's the simplest possible elementary particle. And it's that very simplicity that makes it so deeply perplexing from a theoretical point of view. And in fact, this surprise from the LHC, that we've seen the Higgs and nothing else, is actually a very big deal. It's a challenge to the reductionist paradigm. It goes to the sort of heart of how we think we're supposed to explain phenomenon in fundamental physics. And the theorists are profoundly confused about it. Certainly, people like me who spent the first 15 years of my intellectual life doing nothing but thinking about this physics all day long. This is sort of deeply shocking to a point of view about how these problems should be solved that theorists had been thinking about for 40 years. So theorists are profoundly confused about it, but when theorists are really confused, it's obvious what theorists should do. They should go away and think. It's also totally obvious what experimentalists should do. Ignore theorists and put the damn phenomenon that they're confused about under a microscope and study it to death. Okay, so that's the strategy for experiment, is to put the Higgs under a microscope and study it to death. All right, so let's now talk about why the Higgs is special. So why is the Higgs special? So let's go back again to talking about our subject. What is particle physics? To some people, particle physics is about understanding the ultimate constituents of matter. And okay, if that turns you on, all the more power to you. That was never what excited me about particle physics. In fact, I had to overcome this obstacle to get excited about particle physics, because this sounded like chemistry. And I sucked at chemistry, okay? So I didn't want to go to a like slightly, slight cousin of chemistry that instead of having, 100 elements, had 15 particles with funny names, and it kind of bugged me for a little while. It seemed like boring in the same way chemistry did, okay? So apologies to chemists in the audience. That's not what particle physics is about to me. And to me, what particle physics is actually about goes back to the definition of what is a particle. What is a particle? Well, I think if you're a theoretical physicist, a high-energy theorist, you know the answer I'm going to give to this question in a sec. But most people think of a particle as, well, there's a ball. That's a particle, right? Maybe the ball moves this way. That's a particle. I have an electron moving in the z direction, electron moving in the x direction. These are all particles. If you think about what that definition means slightly more fundamentally, particles are deeply connected to both our notions of space-time symmetries and of quantum mechanics. Okay? So the fancy way of saying this is that a particle is an irreducible representation of the Poincare group. But if you want to say it in a more intuitive way, why does space-time and quantum mechanics matter for the definition of particles? Well, first of all, the symmetries of space-time matter a lot. They're just implicit even in how we think about what a particle is. But the fact that we have symmetries like translations, rotations, and boosts is just hardwired into the very words that we use when we say the electron, right? So here's an electron. When the electron is sitting here, we call it an electron. When the electron is sitting 100 meters away, we still call it the electron. Why? Because there's translational invariance in the universe, right? If there was some background we couldn't get rid of in the vacuum, so the mass of the electron changed by a factor of 5 million when I went 100 meters away, there would be no point calling it the electron anymore, right? It would just be a different beast over there. But the universe has approximate translational invariance. In the vacuum, we believe we have exact translational invariance. And so that's why we call the electron in two different places the electron. Similarly, rotations, boosts, we give them all the same name because that reflects the symmetries of space-time. And of course, the quantum of quantum mechanics is crucially related to the existence of particles. And when we think about quantum mechanics, we have to figure out how to take the symmetries of space-time and act them on states. The states are labeled by the energies and the momenta of the particles and some other labels. And an argument going back to Wigner tells us that whatever these labels are, the states that we get have to be acted on by some unitary transformations that implement the symmetries of space and time. And these labels in the end turn out to be labels associated with the spin of the particle. Okay? So there's a crucial bit of physics here, which is a difference between massless and massive particles that we'll come back to again a little bit later, that the story of the Higgs will be all about that. But when we have massless particles, they only have helicity. When they have massive particles, they have all three polarizations. Let's say if we have a massive spin 1 particle. And this difference between 2 and 3 is a huge deal. We're going to come back to this over and over again. But this difference between 2 and 3, 2 polarizations for a massless spin 1 particle versus 3 spin degrees of freedom for a massive particle is not some technicality. It's just hardwired into quantum mechanics and spacetime. Okay? We're trying to represent the actions of especially the boosts, the Lorentz transformations, and that tells us there's this qualitative difference between spin. We'll say it more about it in a little bit, between massless and massive. So from this point of view, particles are reflecting directly the principles of quantum mechanics and spacetime. These are the 2 foundational principles of modern physics, the 2 revolutions of the first part of the 20th century. And particle physics is the continuing study of the fundamental laws of nature that are governed by the still mysterious union of quantum mechanics and the principles of spacetime. And we can summarize much of the progress in the 3 centuries, from the 17th to the 20th century, as a march of reductionism and a further deeper understanding of the role of symmetries in our understanding of fundamental physics. And where we've gotten to today, on the one hand, with the discovery of the Higgs particle as the high point of this entire intellectual trajectory. On the other hand, it's forcing us to take a 90-degree turn into a different set of ideas that have nothing to do with these things anymore, and that we have to learn what to do to go beyond them. So I want to say a little bit about what the logic is that we've now learned to understand how we go from these basic principles of relativity and quantum mechanics to the structure of physical laws. I'm doing this partially because I think it's a story that's not widely appreciated in most of the physics community. It's one of the really spectacular insights of the past 30 or 40 years that we can really go directly from, you can imagine locking up a bunch of theoretical physicists in a room, handing them the laws of relativity and quantum mechanics, say go, give them lots of graduate students and food and things like that, right? And get them to work, and they'll come out and tell you what the laws of nature can possibly look like, compatible with these 2 major principles. And it's shockingly restrictive what the laws can look like, okay? If you lock these theorists in a room, close the windows, don't let them see what the world looks like outside, and just say that you're allowed to talk about relativity and quantum mechanics, these 2 principles, then they would first say, in the reductionist paradigm, they want to go to very short distances to describe what the laws of nature look like first, using this reductionist picture. Very short distances in quantum mechanics means very high energies. So we're going incredibly high energies. So surely we should be able to neglect the masses of any elementary particles to first approximation. So the first thing you do is decide that you're talking about the interaction of massless particles. Okay? Now you want to take the interaction of massless particles compatible with relativity and quantum mechanics, and here is where the shocking restrictions begin to come in. Okay? It turns out that if you have relativity and quantum mechanics, and restrict yourself to talk about the dynamics of massless particles, you find that whatever the ultimate laws of nature are, we have no idea what they are. Whatever they are, there's gravity. Whatever they are, at long enough distances, it's guaranteed that we'll have elementary particles whose dominant interactions are where 3 meet at a point in space-time. That's one thing. And 2, there's a tiny menu of allowed spins these particles can have. They can have spin 0, 1/2, 1, 3/2, and 2. That's it. Okay? And remarkably, for example, you find out that they would tell you this spin 2 guy is very special. You can only have 1 of them. You can't have 2 of them. Furthermore, this interaction strength that it has with all other particles has to be universal. It's gravity, of course. They haven't looked out the window. They don't know about falling elevators and Einstein and all the rest of it. But they discovered that one of the consistent possibilities is what turns out to be general relativity, even though they've never heard of general relativity. They just know special relativity and quantum mechanics. Okay? But this is one of the things that comes out. And then you can have a bunch of, up to 8 of these spin 3 particles. That's pretty interesting. You can have some number of these spin 1, but they turn out to have the very special structure. It's Yang-Mills theories, but they don't know that. This just comes out of their analysis of what's allowed with relativity and quantum mechanics, and so on. Okay, I've colored in black here the elementary particles that we sort of knew existed in nature before July 4th, 2012. Okay, before July 2012, we know about the graviton, we know about spin 1 particles like gluons and photons and so on, to the Yang-Mills structure, spin 1/2 particles like electrons, top quarks, and so on. And we had not seen nature yet take advantage of the possibility of elementary spin 0 particles or of elementary spin 3½ particles. That was the state of affairs on July 4th, 2012. All right, so this is the claim that these are the allowed theories that we can have. And I just want to give you just a sketch of an argument of how we can know this. I do this partially also because this colloquium is associated with this wonderful school on scattering amplitudes. And this is one of the beautiful things that we learn about nature, thinking about the fundamental simple properties of scattering amplitudes. So let's imagine to begin with that you're trying to restrict from first principles what the interactions between elementary particles can look like. So maybe the first process you would think about, the simplest process, is a scattering process where two elementary particles come in, they hit each other, and they go back out in some way. And let's imagine what the quantum mechanical amplitude for this process could look like. If you don't know anything else, it would be a function of the center of mass energy of the collision, and maybe the angle with which the particles come out, right? So there's two variables, the center of mass energy and angle, and this looks complicated, right? I mean, it's a function of two variables. If I know nothing else, it's a complicated function of two variables. So this problem seems too hard. I can't determine it from first principles. But there's a slightly simpler problem that you can determine from first principles. This problem is so simple that most people don't think about it when they think about amplitudes. But it's the following. Imagine you have a massless particle now coming along, and I want to talk of the amplitude for this massless particle to split into two other massless particles. Now, by energy and momentum conservation, if the particles are massless, the only way the splitting can happen is if the two particles that are going out are exactly collinear with the particle that's going in. So that means that there is no room for angles in this problem. There's no dependence on the analog of angle. That was one of the variables that we had before, right? What about dependence on energy? Can it depend on energy? Well, beforehand, we had center of mass energy. But here, we just have one particle splitting into two. So could the answer depend on the energy of this particle? No, it cannot, because you go to a different frame of reference and its energy changes. Okay, so it can't depend on any angles, and it can't depend on any energies. What can it depend on? Nothing. Okay? In fact, it's entirely 100% determined by the symmetries of the problem. The only thing it can depend on are the spins of the particles, their polarizations. And the dependence on the polarizations is completely determined by Lorentz invariance, basically translations and Lorentz invariance. Okay? So that's remarkable, that this three-particle amplitude up to the actual strength of the interactions is 100% determined by the principles of spacetime. Okay? So 2-to-2 scattering, complicated, depends on two variables. Three-particle scattering, totally nailed. Doesn't depend on any variables at all, so up to the strength of the interaction, it's completely nailed. Now that gives a huge constraint on what the 2-to-2 scattering can look like. Okay? The 2-to-2 scattering, of course, it has the two particles in, two particles out, but it should be possible to develop a resonance when the mass of these, when the energy of these two particles adds up to make the intermediate guy here also a real particle that could be produced. Okay? So if that happens, you know that it's like forcing the system on resonance. So the amplitude should blow up. It gets a resonance. But in the neighborhood of how it blows up, it has to actually subdivide into the amplitude for producing this intermediate particle E on the inside, and E going back out and decaying to C and D on the outside. This fact that in the neighborhood of the resonance, we have to be able to interpret this blowing up amplitude as blowing up in this pattern of this guy, followed by the blow up, which is the long distance propagation, followed by the decay on that guy. This is directly coming from the principles of quantum mechanics. So we have space-time, goes into fixing the structure of the interactions. We have quantum mechanics that tells us in the neighborhood of where these amplitudes blow up, they have to subdivide. They have to factor into pieces, simple pieces in this way. And now this turns into a mathematical problem. Okay, so if you go to, after 1 year of grad school or 1 week of lectures at the summer school last week, you know how to turn this into a sharp mathematical problem. It's a mathematical problem that reflects the principles of space-time and quantum mechanics. You shove it in, and now there's a little quadratic equation you have to solve. Okay? And it turns out, so I'm skipping telling you the steps of that, although it was done in this school last week, that the answer for this is that if you have interactions, these basic interactions that are 3 points coming together in space, then these numbers are just, they're totally nailed up to the strength of the interactions, but the only allowed spins that you can have are particles of spin 0, 1/2, 1, 3/2, and 2 with all those properties that I was telling you. The spin 2 has got to be unique. The spin 3/2 can only exist if nature has a copy for every spin 0 particle is a spin 1/2 particle, for every spin 1 particle is a spin 1/2 particle, and so on. Okay? For every boson, it has a fermion. That's the only way you can have consistent particles of massless spin 3/2. That's a structure that's known as supersymmetry. That's one of the reasons theorists have been excited about supersymmetry for decades. It's, in a sense, the last thing that nature can do compatible with its grand principles that we've not yet seen it do. But that's something that's possible. We've not yet seen according to these rules. And then, like I said, this has got to have the Yang-Mills structure. And these are the things that we had seen before. Okay. So what about the Higgs? All right, so I've just told you that, that essentially the principles of relativity and quantum mechanics make the structure of the laws of nature essentially inevitable. Okay? If we're talking about massless particles, there's only a tiny menu of possibilities that are allowed. All you can do, the spin 2 is unique. All you can do, you can have at most 8 of the spin 3/2. You can decide to have them or not. And then the spin 1 has got to have Yang-Mills structure. You have to say which group. And then you have to say which content for the fermions and so on. But it's just a discrete menu of choices and a strength of interaction strengths. That's it. You compare that to the picture of the laws of nature from Newton that has a continuous infinity of possibilities all over the place. And we've had a dramatic reduction in what you're allowed to talk about for consistent laws of nature. So what about the story of the Higgs? The story of the Higgs is, in a sense, filling in an implicit first step that we did to get going in this story that I was telling you about. So it's kind of like it's a footnote to this story, a very important footnote to the story that I was telling you about, which is that in step 1, we said, oh, let's go to super high energies where we can ignore all the masses of the particles. All right? That certainly seems to kinematically make sense. If you go to incredibly high energies, if E is much, much bigger than the rest mass, clearly the rest mass doesn't matter. You think kinematically it doesn't matter. However, there is an amazing difference, I alluded to it already, between massive and massless particles with spin. Okay? And here again, both space-time and quantum mechanics matter. When you have a massive, let's say, particle that has spin 1, it has 3 spin degrees of freedom. And believe it or not, this really comes from these formal considerations of how you realize the symmetries acting as unitary operators on the states, blah, blah, that you're supposed to do, but it's also very intuitive. No matter how a particle is spinning, let's say a spin 1, and no matter how it's moving, you can always boost to a rest frame where it's at rest, right? And in that frame, now, because of rotational invariance, you can tilt your head, and depending on how you tilt your head, you can see it spinning in 3 different directions. So that means that it's inevitable that a massive spin 1 particle must have 3 spin degrees of freedom. Okay? What about a massless spin 1 particle? Where's the problem? Because of relativity, I can't boost to a frame where it's at rest. I can't make this argument. So I can't say I go to a frame where it's at rest and I tilt my head and I see it go in every possible way. What can I do? Well, I can talk, for example, about its component of spin in its direction of motion or opposite to its direction of motion. And let's say it's spinning in its direction of motion. No matter how I tilt my head, I'll see it always spinning in its direction of motion. Okay? So from here, I can only conclude that a massless spin 1 particle has 1 degree of freedom. Not even the 2 that we're used to talking about, the 2 polarizations, only 1. We normally get 2 for the particles that we see in nature because of an approximate parity symmetry in nature. So a parity would interchange what you mean by the helicity. So if you have one helicity, you should have the other one. That's not even a universal law. It's not true for the fermions. Okay? So it's not true for neutrinos, for example. Okay? So the different helicities of the fermions in our picture of the standard model actually are different kinds of interactions. Okay? But in any case, let's just loosely say for photons and gluons and so on, and gravitons, it's certainly true. They end up having 2 helicities. It's really 1, but it's doubled because of parity. Okay? But in any case, 2 is not equal to 3. Okay? So there's just a strictly different amount of degrees of freedom in a massless spin 1 particle than a massive one. And what matters here is quantum mechanics, is relativity, because you can't catch up with something moving at the speed of light, and quantum mechanics, because that's what's quantizing the spin. Okay? So as simple as that. Relativity in quantum mechanics means there's this discrete difference between massless and massive. So that means when we say we're going to high energies, we can ignore the mass of the particles. It's not quite true, because the number of degrees of freedom is discontinuously different between massless and massive. It means when particles have spin, they can't be a little bit massive. It's like being a little bit pregnant, okay? You can't be a little bit pregnant, as many people know. All right, so that's the story of the Higgs. What you need, therefore, is if we have a pattern of massive particles that we see in nature, and before we'd seen the Higgs, there were in our description of nature, in the weak interactions, I won't go through it in detail. If you know the story, you know it. If not, it doesn't matter that much. We have massive spin 1 particles all over the place in our description of the elementary particles. But what we know is if we go to incredibly high energies, we have to have this extremely locked set of tiny menu of possibilities that we talked about, controlled by relativity and quantum mechanics, right? The question is now, how do we get there? How do we get to the incredibly high energies? And we can't just take the particles we see and just continue them and ignore the masses. If we did that, we'd just find that we did just not get the menu that we needed up there. The number of degrees of freedom was just wrong. You needed extra degrees of freedom to account for the extra components. The extra third component of the massive spin 1 particles, they had to also fit into this picture that I told you of the general structure of laws that you're allowed to have for massless particles. And in order to do that, we needed to have something extra, something beyond just the particles that we had seen before. The absolutely incredible thing is that all it took was a single degree of freedom, one particle. Just a single particle was all that's needed in order to add to the things that we've seen before, such that taking that one particle together with everything else, then at incredibly high energies, gave us one of these very locked pictures that we talked about what the structure of massless elementary particles can look like. That's the real story of the Higgs and the Higgs mechanism. Those of you who have seen other versions of the story, maybe you've heard words like symmetry breaking and potentials that look like this, and some fluid that fills the universe or a condensate that fills the universe, and I'm sorry to tell you, this is mostly wrong, okay? Certainly the fluid that fills the universe is really terribly wrong. If you've heard that, you should please forget about that, because that sounds a lot like the ether. There's always a 12-year-old kid in the audience who said, isn't that like the ether? Didn't you physicists learn anything? And then you say, yes, yes, we know. It's not it's something that fills the universe that's not like the ether, so that's not very satisfying. But even these pictures of symmetry breaking and the mechs and half potentials, I think if you come back in 100 years, people will say that's one nice way of talking about it. It's not the only way of talking about it. It's not the deepest way of talking about it. What I've told you today is, I think, essentially the deepest way of talking about it. The Higgs was needed to allow us to consistently interpolate between the world of slow, massive objects with spin at low energies to this crystalline, perfect, locked world of massless particles at high energies. And the extraordinary thing is that all it took was 1 degree of freedom in order for allow us to do this. Now, this happened by nature making use of one of the possibilities it was allowed to use. It was allowed to have elementary particles of spin 0. We'd never seen nature make use of elementary particles of spin 0 before. And so the belief in these general principles of relativity and quantum mechanics really paid off. But that's the first most invariantly interesting thing about the Higgs. It's the first really new elementary particle we've ever seen. It's our first example of an elementary particle with spin 0. In a sense, it's the simplest possible elementary particle. It has no properties other than mass. It has no charge, it has no spin, it has no properties at all other than its mass. And as I'm now going to explain, that's what makes it so confusing to understand. But before doing that, so that's sort of where we've gotten to today. So now I want to back up and situate the rest of our discussion in what some of the very large-scale theoretical challenges are to our understanding of nature in this century. And there are 2 issues that I want to talk about. One of them is that there are very good reasons to believe that the notion of space-time has got to be replaced with some deeper ideas. And this is very strongly connected to clear theoretical evidence we have already that the idea of reductionism is just wrong. Okay, we have to, the basic paradigm, the laws of nature are understood at arbitrarily short distances, and then everything emerges at longer distances. Because of gravity and quantum mechanics is essentially wrong. So that's pretty dramatic, because we have to figure out what to replace it with, in addition to replacing space-time with more primitive principles. And something a lot closer to home is we don't have a good understanding to the very simple question, why is the universe big? It's maybe one of the most basic facts about the world, that the universe is big. The universe is big, you and I are big, but we're made out of small things. Atoms and molecules are tiny, and the laws of nature are given at much, much tinier distances still. And it turns out to be very mysterious why the universe can be macroscopic. And one of the reasons that it's very mysterious is that in quantum mechanics, there are more and more violent quantum mechanical fluctuations that get increasingly violent as you go to shorter and shorter distances. That would naively make you think that there's crazy fluctuations going on here and there and there. They're all independent of each other, and that it makes it impossible to imagine that some kind of macroscopic order emerges out of this violent, roiling quantum mechanical mess at very short distances. And yet, here we are, nice big universe, you and I are big, the Earth is big. I'm going to explain why this is a question and say what the Higgs has to do with it. But I want to emphasize that really new ideas are going to be needed to make progress on these questions beyond the paradigms of space-time and symmetries. So let me first talk about this business about the doom of space-time, but I'll talk about it in a somewhat different language that emphasizes the strange feature that it mixes up what we think about as short-distance and long-distance physics, or ultraviolet and infrared physics. So let's say you're trying to probe short distances. Because of quantum mechanics, you need, and the uncertainty principle, you need higher and higher energies. That's the irony, that to probe the tiniest distances we've ever probed in nature, we need to build the biggest machines that we've ever probed in order to do so. Okay, so we have to get 27-kilometer round things to probe the distances of 10 to the minus 17 centimeters at the LHC. But in principle, if I want to keep going to shorter and shorter distances, I just need a bigger and bigger machine, and I can do it to arbitrarily short distances, right? Well, this keeps going for a while, but eventually it stops. And it stops when you end up putting so much energy into such a tiny region of space that you can't ignore the effects of gravity anymore. Putting a huge amount of energy into a tiny region of space is equivalent to putting a huge amount of mass in a tiny region of space. And what do you know happens? If you put enough energy into a really tiny region of space, you're going to collapse the region into a black hole. And that makes it impossible to learn what's going on in there. Right? So you're trying to probe what's going on at really tiny distances, and the very act of doing so makes it impossible to probe what's going on at shorter distances. What happens if you get frustrated by this and build an even 10 times bigger accelerator? What do you think happens? You make an even 10 times bigger black hole, right? Because the black hole mass gets even bigger. So you see, what happens as you go to super duper duper high energies is you start probing longer and longer distances again. Not only not true, you can't go to shorter distances, and it stops, and actually you keep going to higher energies, you start returning to longer and longer distances again. The scale at which this happens is the famous Planck length, around 10 to the minus 33 centimeters. But past that point, the energies are 10 to the 19 giga-electron volts. That's 16 orders of magnitude higher than the energies that we have at the LHC. So it's not a practical issue yet. But it means that we already know that this standard reductionist picture of the world, that things are given to us at ultra-short distances and emerge at long distances. If you're a theoretical physicist, this is called the Wilsonian effective field theory paradigm, about the way to think about the world. It's a way to think about the world that has worked in every part of physics that we know, and especially in condensed matter physics. Our condensed matter colleagues love this picture of the world. This explains why you can have the same different materials made of the same kind of stuff, same molecules, atoms, but in different arrangements at long distances that can give rise to dramatic different kinds of physics, even though ultimately it's the same sort of Schrodinger's equation at the bottom for everything, right? But that's the idea. There's a sort of reductionist picture that goes all the way down, and then all sorts of wonderful phenomenon emerge at longer scales. Okay, that leads even some people, some condensed matter theorists even think that maybe the universe is some kind of fascinating metal, some kind of interesting structure that emerges, and things like the standard model gauge fields and chiral fermions and all the things that we see might be emergent properties of a material like that, some fancy exotic quantum material. This cannot be true. Okay, so the world is not, I like to say, the world is not a crappy metal. Okay, the world is different. And this business about this correlation between UV and IR tells us that whatever is going on is far deeper and more radical than things that we've seen elsewhere in physics. But this argument might also make you think that whatever all this fancy stuff is that's going on will only show up near the Planck scale. Okay, so where gravity becomes important, somewhere near the Planck scale. All right, now let's return to the second set of questions about why there's a macroscopic universe. And there are many aspects to this, but one aspect to the question of why there's a macroscopic universe, even assuming that the universe is big to begin with, the question of why the universe is big to begin with has a name. It's called the cosmological constant problem. Okay? If the energy in the vacuum was much bigger than what we observe it to be, the universe would be curled up to much, much tinier sizes than we observe. So there's a zeroth order problem that I won't spend much time talking about here, about why just the energy density in the vacuum is tiny to begin with. But even setting that much bigger problem aside, once the world is big, the question is, why are big things in the world? Why are you and I big? We'll talk about this in a little bit more detail in a second, but this clearly has something to do with the fact that gravity is enormously weak. If we made gravity much, much stronger, you and I would all be crushed into microscopic black holes, and it would be a very unpleasant world. Okay, so the question of why there can be big things in the world is one-to-one the same as why gravity is so weak. Why is gravity so weak? Because the elementary particle masses are not much bigger than they are. Why are the elementary particle masses not much bigger than they are? Well, the masses, remember, of all the elementary particles we were talking about, that's the story we were talking about before, the footnote for what it took to ignore the masses of the elementary particles. The masses of all the elementary particles are set by the overall scale of the Higgs. That's what brings it all back to the Higgs. So we would need to ultimately understand why gravity is so weak is equivalent to the question, why is the Higgs mass what it is and not 10 or a million or 100 million times or 10 to the 16 times bigger, right? But if we back up from that for a second, let's ask the analogous question for other things. Like, what about the photon? The photon is even massless, right? So why is it not confusing that the photon is massless? Well, I mean, you might think it's confusing. Here's a photon that's coming along, but it can have these complicated virtual interactions with all the virtual particles popping in and out of the vacuum. Why don't these kind of interactions that the photon could have with virtual particles in the vacuum, why doesn't this give the photon a mass? Why doesn't the photon have some inertia as a consequence of these interactions? And the answer is very beautiful. It goes back to the same themes that we're talking about again and again. The photon must stay massless, even if it has all these crazy interactions, because of a very simple reason. 2 is not equal to 3. Okay? No matter what you do, if in any approximation you have a massless photon, no small changes to the problem can give the photon a mass, because it can't take you from 2 to 3 degrees of freedom. It can't give rise to a degree of freedom out of nowhere. Okay? This explains why our friends in condensed matter physics can engineer lots of cool systems that give them things like emergent gauge fields and photons at long distances. All you need to do is sort of get into the basis of attraction of the right kind of material, the right kind of system, and then if it's there, it's there. It's robust. Its existence is binary. It could be there or not be there, but if it's there, its existence is robust. I can't just remove it by making small changes. If I change the density of the material, change the pressure, change the temperature, I'm not going to change the existence of a massless spin 2 particle. Okay? Sorry? The mass of the neutrinos actually have a similar explanation. We can talk about the mass of the neutrinos if we come back to this question at the end. Okay? The same thing is true for gravitons. However, the Higgs is special. And the Higgs is special because it has spin 0. And this logic fails for the Higgs. The number of degrees of freedom for a massive spin 0 particle is 1, and the number of degrees of freedom for a massive spin 0 particle is 1. There is no difference in degrees of freedom between massless and massive for spin 1 particles. And that means that if you look at any interaction of the Higgs with the virtual process in the vacuum, there's absolutely no reason this doesn't give the Higgs an enormous inertia, an enormous mass. Okay? Now, in fact, this argument has explanatory power. It explains why, when you walk around in condensed matter systems, you don't see excitations like the Higgs, just garden variety. You see all kinds of other things. You know, you see things that look like phonons, they look like spin zero particles. Like I said, you can get things like fermions, chiral fermions, gauge fields. These are things that you can engineer in condensed matter systems. No one has seen a Higgs in a natural condensed matter system. Why? Because there's absolutely no reason for it to lie around. Okay? It's unlike the other cases. It's not a binary thing if it's there or not. Minuscule perturbations of the system can give enormous inertia to any Higgs-like excitation that might exist. Okay? What you have to do to see things even vaguely like the Higgs in condensed matter systems is to finally adjust the parameters of the system, like change the temperature, change the pressure, change the parameters, and bring it to a very, very special point where sort of accidentally you finally adjust things to come close to a critical point to see excitations that qualitatively look like the Higgs. But you have to do work from the outside. Garden variety systems just don't look like that. Okay? They're not close to having those properties. This argument explains this sort of qualitative fact about what excitations look like in most of the materials we see around us in the world. The amazing thing is that the relativistic vacuum of our universe seems to have one of these suckers in it. Okay? Even though we've never seen anything like it anywhere else in a state of nature. Okay, so that's absolutely fascinating. We've never seen anything like it before. And if we talk about both of these problems in a little bit more detail, both this famous problem of the cosmological constant that I briefly alluded to, as well as the Higgs, these are both things that are telling us that to understand them, we have to go beyond the sort of paradigm of symmetries. And both problems, when you look at them think about them slightly more detail, theoretically, have to do with this essential difficulty that there's nothing special that's happening. There's no difference in the amount of degrees of freedom or the amount of symmetries or anything as the quantity that we care about approaches to zero, which corresponds to the existence of macroscopic scale. So I just told you whether the Higgs mass squared is positive, zero, negative, makes no difference. It has 1 degree of freedom. The same thing is true for the cosmological constant problem. If the vacuum energy is positive, the universe would look like a de Sitter space. That's what we appear to have. If it's zero, it's flat space. If it's negative, it would look like an anti-de Sitter space. But there's exactly the same amount of symmetry. Nothing is changing as you cross zero. Okay? So somehow, this sort of basic paradigm, on the other hand, this difference between 2 not equals to 3, that was exactly where all these ridiculous constraints on the structure of the laws of nature came from that gave us the fantastic successes of the first 20 minutes of this talk. The inevitability of the laws of nature, blah, blah, blah. All of that was exactly because of this strange, discontinuous difference in the number of degrees of freedom between massive and massless. So that way of thinking about it, things brought us to this super high point in our understanding of the laws of nature. That's exactly the thinking that is now taking us nowhere in trying to understand much simpler questions. Why is there a macroscopic universe? Okay, the question of why did we get a macroscopic universe to begin with? If we got it, if we take it for granted, then everything is spectacular, right? But why we got it is exactly what we cannot understand from these set of ideas that otherwise have brought us so far. All right. So I've told you about these 2 big scale questions, where space-time comes from, the end of reductionism, and the questions about why there's a macroscopic universe. And I think both of these are telling us that we're clearly missing something huge about the quantum mechanics of our relativistic vacuum. Those are the 3 words that are occurring together: quantum mechanics, space-time, and the vacuum. We put these 3 things together, and there's something about this triplet of ideas that we deeply do not understand. And that's part of the business of our subject in the coming decades, is to try to make progress on these questions. And I want to stress that the discovery of the Higgs is absolutely crucial for this story. Because discovering the Higgs and nothing else tells us the following. I didn't emphasize this earlier, but exactly the argument that we talked about, exactly the argument that says that the Higgs should have, it's just, if I said it more qualitatively, the Higgs is being battered about by violent quantum mechanical fluctuations. So in order to explain why the Higgs is where it is and not enormously more massive, by this logic, and I remind you, this logic that has worked multiple times in the history of physics, especially in the last century, so it's not the first time we've tried this logic. This logic would have predicted that you should not see a lonely Higgs particle. That in order to understand the origin of the mass of the Higgs, there has to be something that controls these violent quantum mechanical fluctuations. It's like seeing walking, I like to use this analogy, it's like walking to a room and seeing a pencil standing on its tip within 10 to the minus 100 degrees of vertical. And okay, that's a consistent solution of Newton's laws, but if you see something like that, you would wonder, maybe there's something up, there's a string that's hanging from the ceiling, or there's a little hand that's holding it up to stop it from falling over. Okay, so people expected there to be some dynamical mechanism that explained the origin of the Higgs mass, just like there might be a dynamical mechanism to explain the size of the cosmological constant. We knew that whatever was going on with the cosmological constant could not have this character because the length scale associated with the cosmological constant is really big. It's around a millimeter. And we can all do the experiment to see there's no new physics at the millimeter scale. There's no new physics at the millimeter scale by looking. So there's something unusual and strange about the cosmological constant, but a lot of theorists sort of put that aside. They say, okay, that's a much harder problem. We'll come back to solve that later. But the analogous thing for the Higgs, there should be some new physics that shows up right around the mass scale associated with the Higgs particle itself. That's what we've not seen at the Large Hadron Collider. Okay? So seeing the Higgs and nothing else is the first time in the last sort of century since we've been thinking about physics in this way, where we see some phenomenon at scale x whose explanation is not found at scale x. That's a very clear sense in which whatever is explaining the origin of the Higgs mass is coming from a scale that has nothing to do with x, much, much shorter, much, much higher energies. We've never seen that phenomenon before. And so this gives us our first hint that there might be another kind of correlation between very long distances and very short distances. Okay? Had the Higgs problem been solved right around where the Higgs was, okay, that would have been great. That's what we've seen before. The very fact that it isn't gives us another clue that there is a relationship between very short and very long distances that we have not yet understood. And where did we see that before? We see that in the first story of the UVIR connection. Okay? That at incredibly high energies goes back to returning to being something about incredibly long distances again. How that's consistent is a big mystery of how quantum mechanics and gravity works. But we used to think that that's a mystery that only had to do with Planck scale physics. Discovering the Higgs and nothing else is a sufficient shock to the theoretical system that it opens up the possibility that something like that is also relevant much closer to home, not just at the Planck scale, but already at the scale associated with the Higgs particle. So I hope I've now explained that slide that I started with, that the Higgs is the simplest elementary particle. Its very simplicity makes it deeply perplexing. That's the fact that it's the first particle of spin 0 that we see. Spin 0 means that 1 equals 1, so we don't have any understanding for why the Higgs particle should have the mass that it has, and why it's a huge challenge to the reductionist paradigm. And as I said before, theorists are still confused and scratching their heads, and experimentalists should study it to death. So, what should we study to death? Well, the main drama about the Higgs is whether it's really a point-like elementary spin 0 particle. And when I tell you that that's what we've seen at the LHC, I'm cheating a little bit. That's what we've begun to see at the LHC. The picture that we have is still pretty fuzzy. So what does it mean for something to be point-like? Of course, nothing is truly point-like. What it means to even call a particle elementary is always a matter of degree. Because if you have a particle that has some mass m, there's a characteristic size associated with it, given by its Compton wavelength. I'm working here in particle physics units where h bar and c are set to 1. So the Compton wavelength of a particle of mass mh is 1 over mh, or for the Higgs would be 1 over m Higgs. So that's a length scale out here. And so when we say something is elementary, we mean that it doesn't seem to show any substructure on those scales. And that it looks elementary means that it looks point-like to shorter distance scales. It might be that if you go a million times shorter, eventually you'll see something pop up. It'll have some structure, ultimately. And we know it can't look like point-like forever, because when we get down to the Planck length, space-time itself is breaking down. Reductionism is breaking down, blah, 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 right? So when we say that the Higgs looks point-like, it means that it looks point-like compared to the scale of its Compton wavelength. And so the real question is, how point-like is it? And in fact, if we go down one energy scale from the energy scale that we're at in particle physics today, the electroweak scale, if we go down one energy scale to nuclear physics gave us examples of exactly the same kind of object. So pions are the particles that mediate, at least effectively, the nuclear interactions between nucleons, between protons and neutrons. And pions roughly look like elementary spin-zero particles. The pion has a mass of around 135 million electron volts, 135 MeV, but the actual, on scales of 1 over 135 MeV, it looks approximately point-like. We can contrast this with the proton. The proton has a mass of around 1 GeV. 1 over 1 GeV is a length scale of around 10 to the minus 14 centimeters. At 10 to the minus 14 centimeters, the proton looks massively composite. Okay, it's just a big, messy ball around 10 to the minus 14 centimeter big, made out of quarks and gluons. Already at 10 to the minus 14 centimeters looks horrendously composite. Not the pion. At around 135 MeV, it looks perfectly point-like. You've got to go maybe about a factor of 5, 6 shorter distances before you ultimately see that the pion is in fact a composite. It's made out of quarks and antiquarks, and the first hint that it's a composite has to do with its interaction with the rho meson at around 770 MeV. Okay, so the pion over this sort of distance of a factor of 5, 6 actually does look like a point-like particle. And it's not the end of reductionism, blah, blah, blah. It just, just delayed a little bit by a factor of 5, 6. It ends up being composite after all. Very interesting that it's composite. We study it. It has a lot to do with the structure of the strong interactions. Not boring at all, but definitely not the same level of drama of point-like scalars mean all the other fancy things that I was telling you about earlier. Now, what do we know about the Higgs? What we know about the Higgs today, and what we'll know about the Higgs after the LHC is finished running, will tell us basically the same picture. Okay? We know that the mass of the Higgs is 125 GeV, so about 1,000 times heavier than the mass of the pion, and we'll have probed it to distances roughly at the TeV scale. So we will know about how composite it is roughly at 1 over 1 TeV, the same kind of separation. That means that just experimentally, what we'll solid know as a fact, studying the Higgs, by the time the LHC is done running, will tell us it could be about as composite as the pion. Right? That's just not good enough. That's not good enough for us to decide what this actually means. Because it could be, if it's a composite of the pion, that we'll discover it's made out of constituents. Wonderful. That's one road that we could go down, but it has none of the theoretical drama that's associated with the other road if we for sure know it's 10 times more point-like even than that. Okay? So I want to emphasize this very important point for future accelerators, because people talk about measuring the Higgs and precision measurements, and if you're a kind of a zeroth order person, I like to think of myself as a zeroth order person. I'm not a super detailed guy, right? If you're a zeroth order person, you got the zeroth order picture right, first order picture. The rest is just details. So what? You're just going to keep tacking on more decimal places. The problem is that our first factor of 5 or 6 is already zeroth order, because we're trying to decide, is it like a pion or not, right? And so the LHC has not gotten to first order territory, it's gotten to zeroth order territory. Now we've got to go to the first order territory to know, is it like a pion or not? We will not do that with the LHC, full stop. Okay? That's the first thing that we have to do, is figure out, does the Higgs look point-like? And we can do that in 2 ways. We can ask whether it looks point-like to external probes. So to literally look to see if it looks point-like, you'd want to bounce a photon off the Higgs. Unfortunately, the Higgs only lives for around 10 to the minus 20 seconds, so you don't literally bounce a photon off of it, but you would look to see how Higgs decays to 2 photons, or how the Higgs couples to a pair of Z particles, or to other external probes. Okay? So the first thing you want to do is measure how the Higgs looks to external probes to a resolution 10 or 100 times better than what we get from the LHC. Okay? In order to really tell, does it show substructure like a pion, or does it not, in which case we know for a fact that it's completely new territory we have not been in before. You also want to ask whether the Higgs looks point-like to itself, Okay, and this is really cool. It's actually fascinating that there's only 2 elementary particles that can enjoy a self-interaction where no quantum numbers at all change when 3 of them meet at a point in space-time. Every other process where this happens, gluons, electroweak particles, everything else, there's some quantum number that always changes. There's only 2 particles, because of the principles of relativity and quantum mechanics, that can enjoy a self-interaction. Spin 0 and spin 2. So the graviton can also enjoy this self-interaction, but that interaction is so ridiculously tiny, no one will ever measure it. So this is also the very simplest possible interaction we've never seen before in nature. And it'll tell us whether the Higgs looks point-like to itself. All right, so these are the things that we need to do. And we also want to ask questions like, does the Higgs couple to anything else? Okay, other than the ordinary particles that we've seen. So we can do that, for example, by making very precise measurements of the lifetime of the Higgs particle to see if there's any evidence for it decaying to other particles X other than what we've seen. And all these questions are also related to the following thing. If you have seen this Mexican hat type picture before, that I'm not a huge fan of, but anyway, it's phrased in this Mexican hat language. We can say that what we've been doing for the past sort of 40 years in this subject is, first, for a long time, we knew the Higgs or something like it was there, sort of locked at the bottom of this potential. And what we've done, starting July 4th, 2012, at the LHC, is start seeing the first tiny fluctuations around the bottom of this guy. Okay, so that's the parabolic approximation to this potential. Now what we'd like to look like is, what does this potential actually look like everywhere? We have no idea. All we know so far is what it looks like near the bottom. Does it look like that, like in the standard model? Could it have a sort of a cusp at the top there that would have some new structure associated with where you would naively think the electroweak symmetry is restored? This question has everything to do with a very sort of simple question about the early universe. As we go back in time, the universe gets hotter and hotter. So if we then run the picture back forward, there's the phase transition from the place where the electroweak symmetry was unbroken to where it's broken. What was the order of that transition? Was it second order, cross order, first order? What, right? How do we answer this question? Well, we can't recreate the conditions of the early universe in the lab, but by probing the structure of the Higgs potential accurately, we can decide, depending on what the picture looks like, what the phase transition actually did look like as we go back early in time. And this is a question that, in order to answer it, you need to understand physics near the energy of the Higgs, not 10 or 100 times bigger, and to precision, at the 10%, 1% level, because we have to look for new particles that could affect the electroweak transition around the neighborhood of the electroweak scale, not 10 or 100 times far away. And so the new particles have to have some reasonable size coupling to the Higgs in order to be able to affect it in some way. So this question is in really one-to-one correspondence with trying to experimentally probe what the nature of the phase transition was in the early universe. Okay? And finally, if we just go to higher energies, just because to see what's there, then as we look at physics up to scales E max, this probes the violence or the strength of the vacuum quantum fluctuations that affect the mass of the Higgs with a power of E max squared. That's a simple fact about dimensional analysis. I won't explain it in more detail. If you know it, you definitely know it. If not, I won't explain it in more detail. But this just say that as we go to higher energies in the frontier, if we go up by a factor of 10, of course, we have access to particles at a factor of 10 times heavier than we were looking for before. But also, our sort of probe of what's going on with these vacuum quantum fluctuations is 100 times more powerful than it was before. So that squared is an important leverage. Let's see. Can I have maybe another 10 minutes? 10, maybe 15 minutes? I promise. The people laughing know what's, but it's not going to be that bad. All right. I want to make one more point in this neighborhood, because I think we don't emphasize these things enough. What exactly understanding the origin of the Higgs has to do with sort of everyday life around us, okay? And this is just saying in a little bit more detail what I was talking about before. Why can the universe have big things in it is equivalent to the question, why is gravity so weak? Which is equivalent to the question, why are particle masses minuscule compared to the Planck scale? And I just want to put a little bit of flesh on these bones. And this is exercises for the undergraduates or even high school students. I guess there are no high school students here, but this is really high school physics exercises that are a lot of fun to do. So you can ask the question, why is the Earth big? Okay, well, what sets the size of the Earth? The Earth is just the hunk of matter. What's the sort of pressure that keeps you from crushing matter? The pressure keeps you from crushing matter is chemical pressure. It's atomic pressure. It's the energy that it takes to break, a Rydberg over the size of an atom. So these things are determined by the fine structure constant and the mass of the electron. Okay, so all these things are determined in terms of fundamental parameters. And okay, that's good. Now you make the Earth bigger and bigger, more and more and more matter. Now at some point, the mass grows, and the gravitational pressure grows with the radius. Okay, because it's going like gm squared over r cubed. Okay, gm squared over r to the fourth is the, grows like gm squared over r cubed. And so it grows like the radius. Right? So as the radius gets bigger, the pressure gets bigger and bigger. And at some point, the gravitational pressure gets so big that it competes with the atomic pressure, and anything bigger would just liquefy, right? So you can't make bigger sort of rocky objects. So there's a little simple estimate that you can do to equate these two pressures, equate the atomic to the gravitational pressure, and then you'll find how big the Earth can get. And you find the following beautiful formula, that the size of the Earth is exactly bigger than the size of the atom by precisely the ratio by which electricity is strong compared to the gravitational force. Okay? So that ratio is alpha divided by g Newton times the mass of the proton squared. That ratio is around 10 to the 36. And the square root of that ratio is 10 to the 18. And indeed, the size of the Earth is 10 to the 10 centimeters. The size of the atom is 10 to the minus 8 centimeters. And the size of the Earth is pretty much 10 to the 18 times bigger than that. Okay? So the reason why the Earth is big, even though atoms are small, is directly a reflection of the weakness of gravity. Okay? Why are elephants big? Why aren't elephants as big as the Earth? In fact, this argument is better for Brontosaurus. But anyway, why are elephants big? Well, why do you think elephants can't get as big as the Earth? You see, elephants have to walk around, okay? So way before you liquefy the whole elephant, something else happens. As they're walking around, there's enough pressure that you break the bonds along an area's worth of their bones, and that's also bad, because then they fall over, okay? So that means that it's not, you don't need so much pressure to break every bond, you just need to break the area's worth of bonds. And if you go through the same argument, you find it's exactly the same estimate, except because it's an area and not a volume, you get the 2/3 power of this number. So instead of getting to the 1/2, you get 1/2 to the 2/3, which is 1/3. You shove that in. Size of the elephant, this ratio is now 10 to the 12. Okay, 10 to the 4 centimeters is 100 meters. Elephants are not 100 meters tall, but they're 10 meters tall. And this is pretty close to the right answer. And that's because, they don't want to get close to this limit where they're about to break their bones at any moment. Okay, so they want to have a little bit of give. But it's a little bit better for T-Rex and Brontosaurus and things like that. Actually, the Brontosauruses had to live in water, partially because of exactly reasons like this, in order to, they really were close to the limit where they would break their bones as they moved around all the time. All right, so this very vividly shows the reason why there are macroscopic objects in the world is directly because elementary particle masses are small compared to the Planck scale, right? Just 100% directly, and in fact, the sizes are precisely given by these ratios. What about some other things in a little bit more detail? Let's say we took the world as we see it, and we imagined the mass of the Higgs was, the mass squared parameter of the Higgs was slightly more negative than it is. So that means that we broke electroweak symmetry a little more. How would the world change? Well, it turns out that if we did nothing other than take our equation of the Standard Model and we make the mass squared of the Higgs more negative, very quickly the world looks dramatically different than it does now. In fact, if you make the size of the so-called vacuum expectation value of the Higgs only 3 times bigger, the world changes dramatically. What happens in the real world, you see, if you're a kid in high school or in college learning nuclear physics, it's very confusing. I was very confused by nuclear physics when I was a kid. And it turns out because nuclear physics is a fine-tuned, complicated system. And it's confusing why some nuclei bind, some nuclei don't bind, and so on. The reason for all this is just a total coincidence. Okay? if you make the neutron is heavier than the proton. A neutron in outer space decays in 15 minutes. How come it doesn't decay inside nuclei? The reason is that the mass difference between the neutron and proton accidentally is small compared to nuclear binding energies, sort of comparable to nuclear binding energies. If you make the Higgs VEV just 3 times bigger, the down quark gets heavier than the up quark, more heavier than the up quark. The neutron-proton mass difference increases to the point where it exceeds nuclear binding energies, and then they can't even survive in nuclei. Already, if you just make the Higgs VEV 3 times bigger than it is, okay? And that world would have nothing but hydrogen in it. Okay, if you know a little bit more particle physics, if you keep going for a little while, actually the lightest baryon isn't the proton anymore. It has too many up quarks in it. The lightest baryon is the delta plus plus. Too many down quarks, it's a delta plus plus, and that looks like helium. So we'd have 2 boring worlds that are all hydrogen and all helium as we keep going in this direction. The fact that we have all this wonderful, complicated chemistry and so on is just some very detailed, accidental thing, apparently, about where the Higgs is compared to all the other scales in particle physics. So understanding something about the origin of the Higgs is really understanding something about why the world wasn't vastly more boring than it could have been. So that's interesting. What about in the opposite direction? Here I think I'm running out of time, so I won't explain this in detail. But if the Higgs mass squared, if the Higgs did not break electroweak symmetry, the world would also be very different. This is actually a great exercise for graduate students in particle physics to understand this slide, because even in a world if the Higgs mass squared was positive and not negative, we'd still have electroweak symmetry breaking from the quark condensates in QCD, but the W and the Z masses, instead of being around 100 GeV, would be around 100 MeV. We'd still have fermion masses that'd be vastly lighter than they are. So things would be different. You know, the atoms would be meters big rather than the size they are now, but still, you'd have a reasonable-looking world naively, but a dramatic thing would be different. There would be no baryons in this universe at all. There is a famous process in the Standard Model that violates baryon number, but which is incredibly suppressed because electroweak symmetry is broken at scales large compared to the QCD scale. This famous Faileron process would be totally unsuppressed in this other world, and there would be nothing to make structure out of at all. The world would be entirely made out of neutrinos, and it would look absolutely nothing like the universe that we see around us today. So in either direction, we make tiny variations in either direction, what the world looks like dramatically changes. So understanding something about the origin of the Higgs is telling us something about this. All right, so this entire colloquium, I spent longer on this than I thought I would, but everything so far has been about why the Higgs is special and why studying the Higgs to death is special. I just want to say a few things about other things beyond the Higgs and other things that we can learn by going to higher energies. So one of them is that if we go to much higher energies compared to the electroweak scale, something interesting begins to happen that we have not yet seen. So we know that if we go to incredibly high energies, we're supposed to have the restoration of electroweak symmetry. And one of many things that should be associated with this is that we should see something that looks like the classical radiation, but electroweak radiation, okay? Now, how do you think about radiation? Well, I mean, if you're a classical person, radiation is just this picture. You know, you have a bunch of charged particles coming in, something collides, some acceleration happens, the charged particles are going out. And why do we get radiation? It's simply because the Coulomb field, which naively, if the particle is going straight, there's some Coulomb field associated with it. If the particle trajectory bends, then far away by relativity, you can't know yet that the Coulomb field should be different than the one it would have had if it kept moving in its direction of motion. Super far in the future, of course, you should know that it's related to the Coulomb field, the new Coulomb field that it has going out in the direction that it's going in. And so you have to match these 2 different Coulomb fields. And so this is a picture in Ed Purcell's electrodynamics book. There's a shell where you have to switch from one Coulomb field to the other, which is where the radiation lives, okay? And so that's a very simple picture, and that's why what the radiation looks like is either beamed in the direction of the initial state and the direction of the final state, because that's where the sort of kink happens in where these 2 Coulomb fields have to meet up with each other. Okay, so that's a classical picture of radiation. The quantum mechanical way that we talk about it is in the language of Feynman diagrams, and radiation is associated with just emitting many photons, okay? So very naively, if you know that the strength of the fine structure constant is a small number, like 1 over 137, you would think that the probability or amplitude for emitting more and more photons would be more and more small, right? So why do we nonetheless emit lots and lots of photons? Well, there's a figure of merit. There's a figure of merit that tells you when you transition from sort of single photon emission to a picture of classical radiation. And it's the following thing. It's known as the Sudakov logarithm. It's when alpha multiplied by the logarithm squared of the typical energy of the radiation divided by a typical mass scale in the problem becomes of order 1. When this quantity becomes of order 1, then you transition from a picture of single photon emission to genuine classical radiation. When does this happen for the electroweak interactions? Well, the typical mass scale is the mass of the W or the Z particle, and the energy scale is around 10 TeV. So if you want to see in collisions, when you start seeing essentially classical electroweak radiation, we have not yet seen it at the LHC because of this phenomenon of alpha log squared, you've got to get up to about the 10 TeV scale. Okay, so 10 TeV scale is where you start beginning to see really electroweak symmetry restored and behaving like it should. And of course, it's novel because it's unlike QED, we see all the non-abelian phenomenon associated with the splitting of W and Z particles as well. All right, so that's another qualitative phenomenon that we'd see if we go a factor 10 higher energy. We really start seeing how electroweak symmetry is actually directly restored. What about particles beyond the Higgs? And here I want to say absolutely 100% it is not guaranteed that we'll see particles beyond the Higgs. Having discovered the Higgs, we have completed a picture that in principle makes self-consistent sense. There's no argument either theoretically or experimentally that it must break down until we get close to the Planck scale somewhere. Okay, so there's no guarantee that there are new particles beyond the Higgs, and that's why in talking about future accelerators, people very properly, from my point of view, have really emphasized the things that I've emphasized in this talk, what we'll learn about the Higgs and some other things besides. But I do want to stress that there are well-motivated pictures, and many pictures that were proposed and actively studied long before the LHC. So it's not a matter of people changing their tune after the theories have been ruled out, moving the goalposts. These are things that people were already actively talking about before the LHC that are in perfectly fine shape. They still make predictions. They're not been ruled out by the LHC. In fact, some of them have gained a tiny bit of support from what we've seen from the LHC. And in these pictures, there are good reasons why the LHC would have missed new particles, but that a 10 TeV collider would see them, and not 100 or 1,000 or 1,000,000. So it's not a matter of continuing to move the goalposts, but there are reasonable pictures where we would have expected to not see physics at the LHC, but see physics at the 10 TeV scale. So maybe the most canonical example is dark matter. So a lot of you have probably heard about WIMP dark matter. And there's even some sense out there that WIMP dark matters are in trouble or have been ruled out by experiment, and a lot of activity in particle physics phenomenology is looking at a 90 order magnitude parameter space for where dark matter could be for everything other than WIMPs. And that's great activity. I'm very happy that people are doing it, but it is absolutely false that WIMPs are in trouble. Okay? In fact, the very, very simplest model of WIMPs, the very first ones that anyone would have written down, are beautifully alive and well. Okay? If the W in WIMP really stands for the weak interactions, these are supposed to be weakly interacting massive particles, then from day one, when you propose these ideas, you could make a prediction for what the mass should be in order for the dark matter particles to have the right thermal relic abundance. And the mass, for example, if the dark matter was an electroweak doublet particle or an electroweak triplet particle, was never in the neighborhood of hundreds of GeV. It would be 1 TeV if it was a doublet or 3 TeV if it was a triplet. Okay? Furthermore, the direct interactions that these particles could have with matter, for very simple reasons, are just tiny, for no reason for a theorist hiding the particle or doing some clever manipulation to avoid detection. Just out of the box, they have tiny direct detection cross-sections. So these particles are too heavy to make it the LHC, And their interaction with material in direct detection experiments is just tiny. The cross-sections associated with these WIMPs are around 10 to the minus 47 centimeters squared, which are near the famous neutrino floor of the direct detection experiments. They might see these things at the very, very, very end of their runs if they're very lucky. Okay? All right, and these are the very simplest models. Why were people not talking about these simplest models for 30 years? Because people wanted to have new particles to explain the origin of the Higgs. Those new particles should be near hundreds of GeV, not near TeVs. So in those pictures, and the dark matter tends to be the lightest particle in this new sector. So if the lightest particle is at 1 or 3 TeV, there's no way in hell it's explaining the origin of the Higgs the way people wanted to. That's exactly the big surprise. We haven't explained the origin of the Higgs the way people expected to, but that means that we're perfectly free to go back to these simplest pictures of WIMPs and not the more Baroque and complicated ones. It's the Baroque complicated models of WIMPs that have been ruled out. The very simplest models are perfectly alive and well, but the simplest models could not have been seen at the LHC and have not yet been seen in direct detection experiments. Beyond dark matter, but actually partly motivated by it, there are other pictures for physics beyond the standard model. If I had longer, I would spend quite a bit of time talking about this slide. My own personal picture for what's going on with the world since well before the LHC, back in 2004, 2005, was an unusual version of supersymmetry. An unusual version of the supersymmetric standard model where the spin zero partners of the standard model were 100 or 1,000 times heavier than the spin a half partners. The spin a half partners, the gauginos and perhaps the Higgsinos, would have to be down at the down at the TeV scale in order to account for dark matter, but the scalars could be much, much heavier. And this picture was already talked about back in the mid-2000s when I first gave talks about the subject. I was yelled at conferences for daring to speak about a picture of the supersymmetric world that might not explain the origin of the Higgs in the standard way that everyone expected that it would. But this is one of very, very few pictures proposed before the LHC which is not dead. Okay, in fact, it's slightly more alive than it was before because it made a very clear experimental prediction that the mass of the Higgs should be between 120 and 135 GeV. And 125 GeV, it's perfectly fine. Okay? So if you put a gun to my head in the middle of the night and say, what I think is going on in the world, this is what I think is going on. And it has a lot of it explains a lot of other things, big things, small things. As I said, it's worth a whole colloquium of its own to talk about this picture of split SUSY. But this is a picture where you cannot make the particles you can make the fermions, 1 or 3 TeV, that's fine. You can make the scalars are 100, 1,000 times heavier than that, that's okay. But you can't make the whole thing 10 times heavier on top of that. The predictions will then be wrong. The Higgs mass comes out wrong. Okay, so this is a good example of something well before the LHC where we expected, roughly half of the parameter space, we might have seen the gluino already. And the other half, we would not. So the fact that we haven't seen the particles is perfectly fine, but we must see things at the 10 TeV scale if this picture is right. Okay? So I again emphasize, none of this is a guarantee, but it's not the case that there's no reason to expect new particles beyond the Higgs. There are some pictures of the world, including pictures that have been talked about well before the LHC, that would predict that more or less what we've been seeing so far is what has happened. We don't see new particles at the LHC, but we might see them next. All right, so there are many other examples like this, but what I want to emphasize is a general point, is that it's the ideas from the 80s and 90s that have been killed or on life support from the LHC. And there's also a narrative that this is like a very humongous shock and no one saw it coming. And this is also not true because there were lots of clues well before the LHC. I'd say a solid minority of theorists, definitely including me, but most certainly not only including me. I'd say sort of 30% of theorists who thought seriously about these things and stared at the data knew there was something wrong with this party line, that for sure we're going to see supersymmetry, we'd turn on the machine, there would be, the background, supersymmetry would be background, we'd have to subtract over everything else. So it's not even that shocking. given the data that we knew ahead of time. It's generally shocking because we've never seen anything like it before, but it's not. But there's clues to it coming experimentally ahead of time. And there are other theories that were proposed in the 2000s at the present that are alive and well, and some that have even gained support from the LHC. So many have good reasons, not just the ones that I told you about, for no signals at the LHC, but new particles at the 10 TeV scale. All right. So now let me end by telling you something about the future colliders. Right. So what? So I think there's an amazing vision here that's been pursued for the past 8 years now, quite actively, for one program which is about big circular machines. Okay? So the idea is to build a big circular collider around 100 kilometers around, a big ring around 100 kilometers around, and in this ring you could do two things. First, you could collide electrons and positrons with a center of mass energy around 240 GeV. That number is chosen to maximize the production cross-section for the Higgs. And by doing this, make millions of Higgs particles in an ultra-clean environment. Okay? You collide E plus E minus, they're elementary particles, and so it's a very clean environment. By doing this, you can probe, you can do these experiments where you do external probes of the Higgs with precision 10 to 100 times that of the LHC. And there is a reach for new particles that goes up around to the mass scale of the machine. Okay, so of course that's not a big number here, so it's more about these position couplings of the Higgs. Later in the same machine, you collide protons. In the same ring, you collide protons up to 100 TeV. For that, you'll want to wait to make the strongest magnets you possibly can. So regardless, you would want to do this first. And everyone's plan now, this is being actively talked about at CERN and also in China. Everyone's plan is to now begin with the Higgs factory and eventually go to 100 TeV collisions. And there are good reasons for doing this. Now, with 100 TeV collisions, you can produce billions of Higgs particles in a messier environment, but still billions is a big number. And that's a big enough number that you could actually discover and measure the triple Higgs interaction to see whether the Higgs looks point-like to itself. We'll barely know if that interaction exists at all at the LHC. That's one of the big goals of the high luminosity program at the LHC is to sort of establish that this thing is there or not. We'll measure it to the percent level at a 100 TeV collider. Okay? And again, the distinction between these two things is that this is a clean environment, this is messy and rich. Colliding protons is messy and rich. That means you have lots and lots of different initial states depending on the configuration of quarks and gluons that you find on the inside. And that's related to the fact that we've got to go to the 100 TeV to probe the 10 TeV scale. The sort of mass reach gives up roughly a factor of 10, given the sort of messiness of the constituents of the proton and in this story. All right, the new kid on the block that I'll say a little bit about are muon colliders. And if they're possible, if muon colliders are possible, they absolutely rock. This sentence has been true for 20, 30, 40 years, but I want to explain a little bit about them. So first, muons are very familiar elementary particles. They have a mass around 200 times the mass of the electron. They decay in around 1/millionth of a second, and they're copiously produced in cosmic rays. There's around 200 per meter squared per second here, right now. Okay, and the idea is to take these particles that decay in 1/millionth of a second and not let them decay, to accelerate them to 0.999999999 times the speed of light, to make them live longer by relativity, and to collide the hell out of them in order to probe the 10 TeV scale. Now, why is it so useful to do this with muons? Muons are an interesting intermediate between electrons and protons. Okay? They are heavier than electrons, which means they're 100 times heavier than electrons, which means when you put them around a circular ring, the power that they lose by synchrotron radiation, the famous synchrotron formula that goes like acceleration squared, has a 1 over radius squared. Okay, as 1 over radius squared, but also a gamma to the 4th factor, so it goes like the energy over mass to the 4th. So if you make something 200 times heavier than the electron, it loses 10 to the 9 times less power per revolution than electrons do. So that's why it's way easier to make muons go around in a circle than electrons. Yeah. Yeah, I'm almost done, yeah. We also we have to collide them with this kind of luminosity. We have to collide them with around 10 to the 34 or 10 to the 35 per centimeter squared per second. These numbers, where do these numbers come from? We want to probe cross-sections around 10 to the minus 17 centimeters squared, and we want to probe them in a human lifetime. on human timescales. So that's why these numbers are coming from sort of probing 10 to the minus 17, 10 to the minus 18 centimeters squared in an amount so we may make thousands, tens of thousands, millions of these collisions every year. And because of this fact, in order to probe the 10 TeV scale with muons, with protons we talk about a 100-kilometer collider because we have to get the protons up to 100 TeV, because there's a factor of 10 that we're losing. But the muons are still elementary particles, so we don't have that same problem. We don't have the loss of energy problem. On the other hand, they're heavier than electrons, so we can probe the same 10 TeV scale with a collider that's 10 times smaller. Okay, so this basic fact about synchrotron radiation, so it's something that's 10 kilometers around. And part of the reason for the new excitement about this is that people are now imagining that muon colliders might be possible in 25 years. That 25 might be very optimistic. It might be 30, it might be 35, but it's not 50. Okay, so there's a binary thing whether you think it's possible or not, but if you think it is possible, if you believe the optimism, then it's going to happen within the lifetime of the people in this room. I mean, I'll be dead unless I go to the gym or something, right? But it's not something that's beyond the horizon of your careers. Okay, it's something that you'll be the bosses by the time it starts happening. All right. And what's beautiful about them is the muon colliders are really two machines in one. They have the advantages of electron-positron and proton-proton collisions. They have the same clean environment and high precision of E plus E minus colliders. So for example, you can produce 10 million clean Higgs particles in a muon collider, but also get to the high energy of the proton-proton collider, which gives a robust probe of the 10 TeV scale physics. And a beautiful piece of physics is that they have a rich initial state as well. They have a rich initial state for exactly the reason we talked about, this copious electroweak radiation. This copious electroweak radiation means that when muons collide, you should not think about a muon collider as just colliding muons. In this collision, you're actually radiating W and Z particles. So the initial state is a rich combination of the muon as well as all the W and Z radiation that surrounds it. When you get to the TeV scale, we're in the neighborhood where it starts looking like classical radiation, so this sort of picture of a beam that's made out of the muon and all of its radiation friends becomes more appropriate. So in the same sense that the LHC is a gluon collider, we can think about the muons as really an electroweak vector boson collider. But unlike the LHC, where this is all mired in the complexities of strong interaction physics, all of this physics is completely calculable by theorists in principle, and we can understand it. So it's a two-in-one machine. We can understand the properties of the Higgs to comparable position to E plus E minus colliders, and we can get this robust probe of the 10 TeV scale. For example, what I was mentioning before, we can easily cover and produce the simplest picture of WIMP dark matter particles in this setup. There's a variety of challenges in making a muon collider happen, which I won't talk about here because I have challenges of ending right now, okay? But anyone wants to hear more about the difficulties with the muon collider as well as the new reasons for optimism, why they can be overcome, we can subvert the system here of the man, and you can ask a question about it, okay? So all right, so let me end by saying that, really end, it's just, but in seriously, my own feeling is that the scientific issues at stake right now are the most difficult and profound ones that our subject has really faced since the epoch of relativity and quantum mechanics. And that we have to have real vision and ambition to pursue these questions. And we have to be more and not less aggressive about pursuing it. And I think the most important experimental actor in this subject, the most important things that we can do to get new information from nature, we've tried as theorists a lot, but we're confused as theorists. I hope that's clear. We need actual new data from nature. And the best thing we can do is go to higher energies in the region in some of the ways that I outlined. So thank you very much, and thanks for your patience.
So
this is the first hour and a half talk I've given in a while. I'm feeling pretty good, actually. That's
okay, so we'll have 10 minutes of questions.
All right,
thank
you.
Then we'll have a coffee break for 15 minutes.
Yeah.
And then we'll be back here for anybody who wants to continue discussion with him. And he has more lectures to give, so he's not going anywhere for a few hours.
Yes.
But let's take 10 minutes of questions now, and then we'll have a coffee break.
One.
Yeah, go ahead.
I start? Okay. Thank you for the lecture. So my question is, beyond scale comparisons, cosmology, and SUSY, do you believe the Higgs field could be related in some yet to be understood, not trivial way to gravity in some fundamental sense?
Well, I mean, that's I think one of the things that I was alluding to is that if there's some kind of UVIR connection at play in understanding the origin of the large scales in nature, then somehow all these things are related to a gravity. That was not the picture anyone, I mean, we had a strange picture for a long time. People have known about this funny UVIR fact about gravity for ages. It sure looks like it should have something to say about the cosmological constant problem, or maybe the hierarchy problem, because it exactly subverts the standard Wilsonian paradigm. But people said, oh, it's only at the Planck scale, so can't have anything to do with it, right? And that's why there was this sort of cognitive dissonance that, okay, there is this funny thing that could have something to do with these problems, but will not have anything to do with it at the Planck scale, and then we'll solve these other problems some other way. The fact that the accelerating universe was discovered in the late 1990s, that exploded one possibility, that there's some magical mystery mechanism that was going to make the cosmological constant zero. And seeing the Higgs and nothing else explodes another possibility of a more standard kind of explanation for the origin of the Higgs mass. So now, there could be some radically different picture yet besides, but some kind of UVIR connection is definitely an alive possibility for what might be explaining this. And then it's very likely to have something to do with gravity. But this is not meant to be as a sharp statement at all. So this is a speculation, just to be very, very clear. It should be very surprising that it has anything to do with gravity. On the face of it, it should have nothing to do with gravity at all.
Right at the start, when you made that argument about the three-point
Yes.
interaction, and how critical it is for that argument to assume there's no four-point contact interaction?
Not critical at all. Not critical at all. That argument is really a totally invariant argument. When you have contact four-point interactions, those are things that we cannot determine purely in terms of symmetries, and instead we can do a power series expansion. We can, but it's a very special thing about the three-point interactions. The three-point amplitudes are completely determined by symmetries up to the scale of the interaction. Yeah. You might be thinking, is that three-point interaction that I talked about related to the three-point coupling in the Lagrangian? And the answer is it's related, but it's not the same thing. What we're talking about here is the literal on-shell amplitude, and not the object in the Lagrangian.
Hi, yeah, thanks for your lecture. It was very clear, but so my question will be somehow I'm confused because of your cleanness.
Oh, good.
So you start your lecture saying that we should have, without experiment, it was impossible for intelligent artificial, for IA, or for only the theorists, to devise the standard model, or
yes,
the knowledge that we have.
Yes.
Then you put some graduate students and put some food there,
yes.
and
yes.
they make out all of the good things that we know.
Yes, that's right.
and somehow
I see the contradiction you're talking about. Yes, yes. Well, you know, theorists are simultaneously the most arrogant and the most humble creatures on the planet. So that, well, because the things we understand incredibly well, and the things that we don't understand, I hate to channel Donald Rumsfeld, but the things that we don't understand, we also understand very well what we don't understand. So we can say very sharply what the mysteries are that we don't understand. What I said before, but I think you were alluding to the historical comment that I was making, and there, so much of the confusion of the dynamics of the standard model had exactly to do with what happens as you go to long distances, okay? As you will go to long distances, there was a sort of two big confusions, or the two big things that had to be discovered, the spontaneous symmetry breaking and confinement, okay? So those are two things that were precisely where the world at long distance differs in some qualitative way with what you see at very short distances. So what I was telling you about, what the theorist would get locked up in a room without thinking, is what essentially the classical or semi-classical picture of massless particles weakly interacting with each other can look like. It's an amazing fact that that's essentially God-given from the principles of relativity and quantum mechanics. But it's that part of the physics that's totally understood. And then how that evolves into long-distance physics has lots of conceptual novelties and things that people had to sort out. And that really needed input from experiment, for sure. And sorry, maybe I can say one more point. I mean, this happens in physics all the time, that theorists are confused for a long time, and then you understand something. And a good thing to do after you understand it is to keep churning over it over and over again until you sort of, to be able to put the thing that you understand in the sort of cleanest conceptual framework you possibly can. So that sometimes will take you quite far from the original way that you understood it. But it's important to do that so you understand in the most geodesic possible way how the principles turn into the part of the physics that you understand perfectly. So that's, and even historically, the argument that I told you was not understood till well after the standard model was established. So it was not even something, it was something, this is one of the quiet revolutions that sort of Weinberg understood 80% of it, and then, you know, this whole amplitudes program has understood it more and more. Different people understood different aspects of it. I'd say only in the last 20, 25 years do we say it as perfectly sharply as I just explained now. But definitely was not available before the standard model was set. Okay, so we couldn't even have inverted the history the way you were imagining doing.
So you hope, I think, that we are in the verge or not, but maybe if we keep building these large things, we will have a different thing.
Yes, yeah.
Beyond.
That's what I was trying to say.
Beyond relativity and quantum mechanics, right? Is this the
yes?
The thing,
I think
right?
so. I mean, I think that's
your
what
argument is that with quantum mechanics and relativity, we can build this so much, and we have this possibility. And now we maybe are in the verge
It's really
of breaking.
the triplet. It's really the quantum mechanics, space-time, and the vacuum. And the special fact that the vacuum has this property that it gives us approximately massless particles in a big flat space. The crazy surprise is that we get approximately massless particles in this big flat space. If we take that for granted, we can go very far. If we step back and ask, where did we get it? We have no idea. So that's why, you know, making progress on this question is not something small, right? And it has a different character answer than the ones that we use so far, where we assumed the starting point. Now we're trying to take a step back and see where the starting point came from, because it's deeply confusing where it came from. It's very interesting that what makes it deeply confusing is not related, it's not unrelated to what made it so powerful in the other direction. It's exactly 3 not equal to 2 business. Okay? It's a 3 not equal to 2 business, which is where all the power came from to begin with, but which is exactly what fails us in trying to understand the origin of the system that we have to study to begin with.
Is there anybody who hasn't asked a question that wants to ask a last question? Okay, last question.
Hi, Nima. So what is the status of the hierarchy problem now? Do we have any help?
Well, I mean, the status of the hierarchy problem is that people thought that, of course, you know, and any professional here knows that I was talking about the hierarchy problem without saying the word hierarchy problem. But the status is that it is a problem. It's a harder problem than it was before. There are some people who say it was never a problem, it was some bullshit philosophical problem. We can have a long discussion about that, but it's most certainly not a bullshit philosophical problem. It is a real problem. It is a real serious problem. It's just that all the ways of trying to solve it that kind of had historical precedents in the past have failed. So that's why it's so dramatic. That's why we're, you know, all the things that have some analogs in the last 100 years don't work anymore. And so there has to be something new. What is that new thing? We don't know. So we can have we can really try as theorists. And we should try. I mean, I try all the time. I haven't written any papers about it. I've actually written one paper about it in the last 10 years. It's not a terrible paper, not a great paper. But it's a very hard problem. It got much harder than it was before, but it most certainly did not go away. And, you know, I mean, I love working on what I'm working on now. It's great. I love so much of theoretical physics. It's wonderful, great stuff. Formal properties of quantum field theory, amplitudes, blah, blah, blah. It's wonderful. But every 3 days, I'm in the shower. I'm like, holy shit, there's a big universe. Why the hell is there a big universe? It's crazy, right? How could you not work on this question? It's totally insane that we're doing all these fancy schmancy stuff, and we don't understand something as big as why when I walk out the door, I can walk out the door, right? You know, that's, right? So it's amazing that problem is still lying around, and someday it'll be solved, someday it'll have a solution, and the character of the solution is going to be, I think, is going to be quite amazing.
Okay, so let's thank Nima again, and then there's a coffee break.